Next up, we have Marianne Touchie, and some of you may know her from her tower renewal work. Marianne Touchie is an assistant professor jointly appointed in the departments of Civil and Mineral Engineering and Mechanical Industrial Engineering at the University of Toronto. Prior to joining the U of T faculty in 2016, she was the Building Research Manager at the Toronto Atmospheric Fund and a postdoctoral fellow in the Department of Civil Engineering at the University of Toronto. Her research focuses on improving the energy performance and indoor environment quality of existing buildings to make them more comfortable, healthy, and sustainable through comprehensive retrofits. Most recently, Dr. Touchie and her colleagues have been studying the interaction between energy performance and indoor building environment quality in Toronto's aging multi-unit residential buildings, including a number of buildings used for social housing. Dr. Touchie teaches undergraduate and graduate courses in both civil and mechanical engineering, including building science and HVAC fundamentals. She's also Vice President of the Building Science Specialist Board and the Vice Chair of the Technical Committee on Physiology and Human Environment at ASHRAE. Marianne, come on up. We can just leave that there for now.
Okay. There's no, I thought my presentation was on.
No, it's not on there.
It's not on there.
It'll be up at here.
Okay, that's good.
You good?
Yeah, okay, great. All right, good afternoon, everyone. Oh, I'm not used to, can normally walk around, but I got to stay by the mic. Thank you very much for having me. I'm really excited to be here today, and it's nice to see lots of old friends. So today I'm going to tell you a little bit about the work that we've been doing on examining the impacts of overcladding in post-war apartment buildings. But before I do, I just wanted to talk a little bit about our lab at the University of Toronto, what we do. So my PhD work was really focused on energy performance in multi-unit residential buildings. And as part of that work, I was doing a lot of field work, monitoring, speaking with residents, and realized, as many of you in this room know, that there are a lot of indoor environmental quality issues in these buildings. And so when I had the opportunity to start up my own lab at U of T, I really wanted to make the focus of what we do on trying to improve not only the energy performance of these buildings, but also the quality of the indoor environment for the people that live there. So we really work on a number of things. First of all, characterizing the quality of the indoor environment in a lot of these buildings. We don't have a lot of information about how these post-war buildings operate, and particularly an area that I'm just starting to get into are newer condominiums as well. And then we do a lot of modeling and testing using the field data that we've collected, ideally going back out into the field and testing new strategies. And then sort of the latter part of our cycle in terms of disseminating best practices. The lab's only been around for a couple of years, so we're still working on some of our initial projects, but that's sort of the end goal, is to then influence design. So really the areas in which we work are really the intersection between HVAC systems and the building envelope, and then of course how the occupants of the building influence both of those components. So today, with this focus on overcladding in post-war apartment buildings, we're first going to have a bit of a crash course on how post-war apartment buildings operate. We'll look at what happens when you tighten the envelope, how that influences building performance, and then what happens when you build tight and then add that appropriate ventilation, so ventilating correctly. And then I'm going to tell you a little bit about what I think is a pretty exciting study that we're working on at U of T. I'll show you some of our pre-retrofit results, but I'll have to come back next year maybe and show you some of our post-retrofit results. And then I'll talk about what our next steps are as well for this study. So anybody who knows me knows I love these buildings. This is actually the building where I did my PhD. I spent a lot of time in post-war apartment buildings across the city, just to get a sense how many people in the room work in this sector and have a lot of experience poking around. Oh, only a handful. Okay, I expected a lot more. Okay, great. So maybe the crash course will be useful for more people than I anticipated. So now I have to preface this. Obviously, every building is different, and we need to take a unique approach to really understand the challenges of each individual building and the occupants in which they live. But generally speaking, this typology has a lot of common challenges associated with it. So first of all, These buildings were built in the 1960s and 70s, so at a time when we weren't really spending a lot of time focusing on energy performance, so minimal levels of thermal insulation, if any. The original windows, usually typical single glazed sliders, very air leaky. They are also different to the commercial buildings, where I'm sure a lot of people in this room spend a lot of their time in. We also have operable windows, so that adds a level of complexity here. We have exposed slab edges, are very typical. So a lot of thermal bridging happening. Also, one aspect of their operation that I don't think a lot of people are aware of is these buildings typically don't have any in-suite heating control. So there are often 1 or 2 temperature sensors used to control the entire building. So how do occupants regulate their temperature? They open and close their windows. That's also how they get access to fresh air as well. So we really can't ignore occupants in a building like this, because they actually have an enormous influence on how the building itself operates. In terms of ventilation systems, these buildings typically operate with what's called a central pressurized corridor ventilation system. So that involves a couple of makeup air units up on the roof that bring fresh air into the common corridor spaces, which in a perfect world are positively pressurized. And then we're relying on little tiny undercuts underneath the suite doors, if they haven't been blocked up, to allow that ventilation air to transfer into the suite. So a lot of things have to go right to make these systems work well. But these buildings, in terms of energy performance, see a pretty similar profile to a lot of residential buildings in Canada, so roughly half on space heating, a quarter on domestic hot water, and then the remainder on all of our other electrical loads. But a number of studies have shown that the operation of these central pressurized corridor systems, or the lack of their effective operation, actually contribute enormously to that space heating piece of the pie. So between 40 and 70% roughly associated with the operation of these central pressurized corridor systems. So let's look a little bit more closely at how they work. So as I mentioned, we have these makeup air units on the roof that in a perfect world are positively pressurizing, evenly pressurizing all the way down the building. But in reality, where these buildings, or any building really, particularly in our climate, are operating under a lot of different dynamic conditions. So we've got the effects of stack due to the difference between indoor and outdoor temperature difference. We've got wind impacts as well. And when you pair that with a relatively loose envelope, remember these people are opening and closing their windows to regulate temperature, and a lot of continuity or connections between the interior zones, so we've got a lot of interzonal air leakage, you end up having, it's really a bit random who is actually getting the amount of ventilation air that they require. So typically near the top of the building, we'll see higher ventilation rates than near the bottom of the building. So we know and we've known for years that these systems don't work, but we typically, to deal with a lot of these dynamic issues, these systems tend to be quite oversized. So a study of about 10 MURBs that were built in the, MURBs, multi-unit residential building, built in the 1990s, I think showed an average of 2.5 times the ventilation air being delivered from the makeup air unit than what was required by ASHRAE 62. So these buildings these systems are oversized. So now that we have a sense of how these buildings operate and some of the challenges associated with operating these buildings as they are currently designed, I just want to take a look at, I'm going to show a couple of case studies that have been done in other parts of the world, one Canadian and a couple in other parts of the world, and then I'll talk about the study that we're working on. So the first one, I'm sure many people in this room are familiar with the Belmont, probably the most monitored and tested building in Canada. It's a condominium, moderately sized, 13-story, 37 suites out in Vancouver that underwent an overcladding process, and RDH Building Consultants has done some extensive monitoring and testing of this building. So that's why I'm using it for this example. We don't often have access to these type of data on this particular building type, but they use tracer gas testing to look at how the air moves throughout the building, and extensive air leakage testing as well. And so one would hypothesize that when you tighten up the building envelope, so you control a lot of that previously uncontrolled air leakage across the envelope, you would think that would have a significant difference on, or significant impact on how air moves through the building. And the interesting thing was they found that post-retrofit, through their differential pressure monitoring, there really wasn't much of a change. And they hypothesized that the reason why was the occupants. So that window operation behavior did not change post-retrofit. And so the impacts of that tightening of the envelope really didn't have the projected impact on how air was moving through the building. So this is a plot taken actually from Lauren Ricketts. This was his master's thesis, and this is one of the papers that they published out of that. And basically the plot just shows, so you've got the building height from bottom to top there on the y-axis, and then the flow rate that they measured. So they used a bolometer to measure the flow rate of the supply air grills in the common corridors on each floor. And they did that before the retrofit and then twice after the retrofit at different temperatures in the purple and the blue. So you can see that the pre and post retrofit airflows didn't really change that much. And so just, again, reiterating what we found before, that this window operation, because of the window operation of the occupants, we didn't really see too much of a change. And then the result, when you actually look at the suite level, was that, so just to orient you on this plot, so we've got our estimated airflow delivered to the suite on the y-axis, and then the various suites that are organized according to building height. So at the bottom of the building on the left-hand side, moving to the top of the building on the right-hand side. So you can see the buildings in the lower half are typically well below the required ventilation rate. Even a couple on the upper half, and then some are over-ventilated. So as I illustrated in the schematic earlier, it's really, some are over-ventilated, some are under-ventilated. You might get one with exactly the right amount of ventilation air, but chances are pretty slim. So we know that overcladding and window replacement can be, or the decision to overclad and replace windows is often driven by the desire to reduce heat transfer across the envelope. So we're increasing the thermal resistance, we're tightening up the envelope, we're trying to prevent that uncontrolled air leakage. And then also to improve building aesthetics. I mean, particularly in private rental buildings, that's often a big driver as well. But we need to be mindful that we're potentially increasing things like the relative humidity, the CO2 concentration, which in and of itself is not necessarily a huge concern depending on the concentration, but can be a proxy for things like odor transfer and smoke transfer and things like that. And so, again, this is what they found out west, looking at some of the data, looking at the dew point temperatures, for example. So they were finding that the dew point temperatures in the corridor were much greater than what was coming from the makeup air unit. So they was indicating some backflow. You're getting some air flowing from the suites back into the corridor, so leading to cross-contamination. Also noticing that they also noticed that the dew point temperatures in the suites were much, much higher than outdoors. So the existing supply and exhaust systems really weren't doing their job to get rid of that, the internal sources of moisture. So something that we need to be mindful of. But at the same time, I mean, we're all trying to save energy. We're all trying to reduce our space heating energy use and cooling. So it's a good thing. But we can't forget about the occupants in these buildings. And I think so often we're focused on just getting to that number. We need to remember that occupants are, I mean, they're going to do everything they can to optimize their thermal comfort and their access to fresh air. And so we need to allow them to do that. So I just want to, before we move on to the second part of the presentation, I just want to remind everybody, I'm sure everyone in this room is well aware that we design buildings for people, but sometimes it's worth just remembering that in our effort to do energy retrofits, remember that these retrofits can potentially have a positive impact on the quality of the indoor environment or no impact, but they can also have a negative impact. And so we need to keep that in mind right from the very beginning when we're starting these processes. So now I just want to share with you two international examples of overcladding retrofits that have been done more by looking at the building as a complete system. So looking at heating controls and also ventilation as well. So one is in Sweden, so that's 6 mid-rise buildings, again, built in the same era as a lot of our post-war buildings in the 1970s. They had a fairly comprehensive retrofit plan. There were 6 of these buildings. They actually only retrofitted 1 at the time that this study was published, but did a fairly comprehensive analysis that included in-suite monitoring of temperatures and relative humidities. They also did comprehensive resident surveys, and they also did some energy submetering as well. So what they found were a number of improvements to the quality of the indoor environment. So less post-retrofit, so with this balanced supply of ventilation, air, and the overcladding completed, there was a lot less odor transfer between suites, smoke transfer between suites was reduced. In terms of the interior temperatures, much more comfortable in the wintertime, so less draft sensation because of that air tightening, and significantly less noise as well, which makes sense. You know, if you improve the windows and reduce that uncontrolled air leakage, you're going to have a lot less noise from outside. And then also reduced instance of health issues, you know, cough and dry throat, headaches, things like that. But one of the things that they did notice was that in the summertime they started to see a bit of overheating, so there's still a little bit of a control issue that we have to deal with there. But on the whole, all of the residents were more satisfied with the quality of their indoor environment, and they were also able to achieve almost a 40% reduction in space heating energy use. So it's possible to do both of those things. It just requires giving residents the tools to tune their indoor environment to the way that they want to without having to resort to things like opening and closing windows. So another retrofit, another retrofit I wanted to talk about briefly was Wilma Courthouse, which is in the UK, and they a little more similar in size to the buildings that we deal with here in Toronto. These larger suites, like larger 3-bedroom suites. So one of the big issues with this public housing building that's different from the way that we do things here, normally residents here don't actually pay for their energy use, but here the energy use was submetered. And so fuel poverty was widespread. So about half of the residents prior to the retrofit would go without heating in order to save money. They would turn their heat off in the middle of the winter. And you can imagine the mental and physical health effects that that had on the population here. So as part of the retrofit, as part of the retrofit process, one of the big pieces was resident consultation. And first of all, getting a sense for what the issues were at the outset. So they had these surveys and semi-structured interviews of the residents before, during the construction process, and then after the retrofit. And so basically, I mean, I pulled out a couple of my favorite quotes. So most of the building was rubbish, the heaters and the windows, a lot of mold growth on the inside of the building, a lot of, again, this fuel poverty issue, incredibly expensive fuel bills that the residents had to deal with. So as part of the overcladding process, as part of the retrofit process, an overcladding was done, triple glazed windows were installed. They actually enclosed some exterior corridor spaces, and they added this balanced supply of ventilation air into each suite. So post-retrofit, again, they went back and interviewed the residents, and it was, I think the average energy savings was per suite annually was something like 700 pounds. So a really dramatic decrease in fuel costs. I think only one respondent post-retrofit said that they still had to moderate their heating energy use in order to save money, but basically everyone was able to now afford to heat their suites to a comfortable level, but dealt with a lot of the indoor air quality issues with that balanced supply of ventilation. So some great international examples, but this is actually a retrofit I was talking with some people at lunch. I'm trying to actually find some examples of this system-level retrofit that involves suite-based ventilation here in Toronto. So if you have any projects, come and talk to me at the break. But we were fortunate enough to be given access to 2 buildings that are 2 high-rise post-war apartment buildings. that are both undergoing major cladding retrofits right now. So one is being overclad, and the other one, overclad with their windows replaced. So that's building A there, 24-story building. And then building B, which is just having their windows replaced. And no suite-based ventilation strategy. The ventilation systems are being replaced, but replacing like with like. So still sticking with that pressurized corridor system. So we really wanted to take a comprehensive approach to this study using a lot of the protocols that have been established in some of these international studies. So rather than just monitoring some of the indoor environmental quality parameters, we also wanted to talk to the residents and get their perceptions of those spaces both before and after. So I created a bit of a flow chart because there's a lot going on in this study. So we basically, we started out with resident surveys in both buildings. We've done some extensive air leakage and airflow measurements in the building. So both component level tests looking at the air leakage of windows and balcony doors and suite doors. And also airflow measurements, so using bolometers to look at bathroom and kitchen exhaust flow rates and the supply air that's coming from those supply grills from the central pressurized corridor ventilation system. And then we supplemented that with some theoretical values from the literature to develop a series of content models where we're basically trying to calibrate that model, although that's been a little challenging, to some of the field data that we collected. We also undertook some tracer gas testing. So we seeded a number of the suites with different gases and used capillary absorption tubes to collect those gases, basically paint a picture of how air moves between the suites and how much air exchange each of those suites is seeing with the outdoors. And then we also seeded the makeup air units to see how that ventilation air is distributed throughout the building. But getting these two things to agree is rather challenging. But the idea was to create this model with which we could then try to model the impact of the overcladding and the window replacements, and then post-retrofit, we want to see how close we were able to get with that modeling. So that's really the purpose of this multi-pronged approach, to see if we can come up with a more reliable way to model this. So some of the pre-retrofit survey results, similar to anecdotally what I had experienced in other buildings and in other from other studies as well. So a lot of the respondents are opening, 40% of the respondents were opening their windows daily. Almost everyone else was opening it once or twice a week. What was interesting was almost three quarters of the residents either said their exhaust system was not working or they did not have one. Now they all have one, so I'm interpreting that as it is virtually useless in their mind. And a lot of residents were bothered by odors and smoke transfer from other suites. And these findings agree with results that we had, a much larger study that we had done, which involved 70 suites across 7 buildings. So this plot, the icons, I don't know if I have a laser here, are cooking, neighbors cooking, smoking, and outdoors. So cooking, neighbors cooking, smoking, and outdoors. So we were basically asking the residents how often they were bothered by this. So the red bar is indicating daily. So over half of residents I said a sample size of 70. This was actually a sample size of 180 suites across 7 buildings. Over half of the residents were bothered daily by at least one of these things. So this is a significant issue. So as I mentioned, the other part of the study that we did was using this tracer gas testing. So because of the window operation, it was difficult to get any precise results from this, but we have some idea of trends. And so the results of the tracer gas testing suggested a direct connection between a lot of suites. So rather than air moving out into the corridor and then into another suite, we were actually seeing transfer directly between suites, which is understandable when you think about some of the mechanical penetrations that could be occurring through the slab. Results also suggested some of this backflow, so actually negatively pressurized corridor, so the air is moving from the suites back into the common corridor, which again agrees with our survey results looking at the detection of odors and smoke from other suites, and agrees with the studies done out west as well. and extraordinarily high infiltration rates. And again, expected because the occupants are opening their windows. So it's nice to see that our field measurement is agreeing with the survey. Sometimes that does not happen. And then the step that we've just finished and needs a bit of a refinement is to actually create a pre-retrofit model of this building. So we, just as a first cut, we were testing, obviously this is a very dynamic system, so we were testing various wind and corridor pressures. But basically in all instances, as soon as we added that overcladding, the level of interzonal air exchange actually increased. So something that we need to be mindful of. And again, another sort of plug for some sort of balanced supply of ventilation air at the suite level. And I'll come back to it, but interzonal air sealing is something that we need to look at and something I'd like to explore. So the next part of the study that we're just embarking on right now is actually trying to model some different ventilation strategies to understand the energy impact of these strategies, but also how effectively we can move air through these buildings given all of the dynamic forces that I had mentioned before. So there's a bunch of different ways to get outdoor air to the suite. So we'll model this base case, as I mentioned, with that central makeup air unit and the pressurized corridor. Look at decentralized makeup air units. So can you split them across the building height to reduce the impacts of stack? One of the buildings that we're working with right now wants to investigate direct ducting of that supply air at the corridor level into the suite. So we'll model that out. If the central system itself doesn't work, then ducting it directly to the suite, I'm not sure how well that's going to work, but we're going to try it out. Using a VAV box at the floor level to, again, try to manage those airflows, dealing with wind and stack. And then looking at sort of the other end of the spectrum, completely decentralized, looking at 1 HRV per suite. So that's what we're just getting started on, but hopefully I'll have some results for you in the next couple months on that. So on the whole, I just want to wrap this all up. I know I've thrown a lot of information at you about these different case studies, but I just want to wrap this up with a couple of lessons, or lessons, thoughts, things to think about, things that we can discuss at the coffee break. So I want to be clear that I'm not saying that we do not need to improve the performance of our building envelope. We absolutely need to do that and take those passive measures to reduce heat transfer and reduce that uncontrolled air leakage. Another element that I think we need to consider, which I mentioned briefly, is that uncontrolled airflow between suites, so that interzonal air sealing, or the idea of compartmentalization. But we need to actually add some sort of active or more effective mechanical ventilation, so some sort of balanced supply of fresh air at the suite level. And then obviously improving system efficiency. But the other piece of the puzzle, which I didn't have time to talk a lot about today, but I think warrants perhaps a whole other presentation, is control strategies. And controlling things with such a large building, with such diverse demands from the residents at a central level does not make sense. We need to be able to provide residents in their suites with control of both temperature and access to fresh air. So that's something that needs a little bit more attention. So, I mean, this all sounds great, but there are a lot of reasons why we don't actually do this. So first of all, we need a goal to work towards. So we often work towards an energy target, but I think we need to really think about targets for indoor environmental quality as well, and have measurable, this is what we're aiming for, and this is a level of acceptance with the residents that we're aiming for. So you can't, you can't model what you can't measure, but you can't get to a goal unless you set it. So we should set the goal. Also, there's an issue with multifamily buildings where we have a split incentive. So often the people that are paying for the capital upgrades are not those that are paying the energy bill. So there are some innovative ways of getting around that. So we just need to be a little bit more open-minded there, and I'm happy to talk to people about that further. A lot of these buildings are social housing buildings, and there are obvious capacity constraints that we need to deal with there. That's definitely a tough one, but there are, well, we'll see what happens after the election, but there is potentially funding available, and we need to just make sure that all the appropriate parties are aware of what's out there, so we can sort of maximize what we can do. I'm going to wrap this up, I promise, so we can have some questions. I think everyone else can read that. Oh, the other thing I wanted to point out was just more comprehensive modeling. So we don't necessarily want to stop at the energy model. We want to look at some of this more detailed airflow analysis, and I know there are a lot of experts in the room who can do this. Just make sure that we're understanding the systems the impact of the systems that we're putting in. So. And yeah, just quickly, I think, again, everyone in the room is aware we have to deal with the effects of this changing climate and a changing landscape when it comes to energy performance. And I think I'm hoping our job will be made easier by pricing on carbon and things like that. So it may make these challenging decisions now a little bit more palatable further down the road, but we'll see. So thank you very much, and sorry I only left you minutes.
All right, do we have any questions for Marianne? Over here.
Hi. This is so cool. I'm so glad you did this. But something I've often wondered is the elevator. Like, the elevator is a shaft through the whole building. I once had a project that we retrofit, and so the top of the elevator shaft was just like Swiss cheese, and you couldn't even open the doors in the lobby, right? So we figured that out as we were starting to occupy the building. But the elevator itself, can't it, like, have you done any work on that? Can't it short circuit the whole pressurization system if it's not properly sealed at each floor, or?
Oh, absolutely. Thank you for the question. Yeah, elevator shafts and garbage chutes and all of those vertical chases, penetrations, absolutely short circuit this. So I think there's a couple of things. One is we need to look at vestibules and things to separate the airflow, separate the elevator from the rest of the building. But also this idea of compartmentalization at the suite level can address a lot of that too. So if each suite is sort of operating as its own airflow entity in the sky, so they have that balanced supply of ventilation air, and there's not a lot of transfer from the corridor to the suite and between suites, I think that can address that issue as well. But I'd also love to hear from people who've dealt with that, because that's a huge problem when you get really high pressures. I know that people get stuck in elevators because of that in the middle of the winter, so yeah. Okay, great, thanks.
Thank you very much, Marianne.